So let's consider the following matrix. It's not hard to see that the characteristic polynomial for this matrix is lambda squared plus lambda plus 1. The discriminant of this polynomial is 1 squared minus 4 times 1 times 1, which is minus 3, is negative. So this tells us there are two complex eigenvalues, which we will call rho and rho bar, which is the complex conjugate of rho. So last time, our observations tell us we should expect this matrix to encode multiplication by one of these eigenvalues. To start out, we're going to compute the eigenspace E rho, just as if rho were a real number. So we'll take the matrix A minus rho I, and we can see that this is rho equivalent to 1 minus rho, rho plus 2 minus 3. In order to clear the second row, we want to multiply the first one by rho plus 2 and subtract. So first, we'll compute rho plus 2 multiplied by rho minus 1. We see that we get rho squared plus rho minus 2. Now, we remember that rho is a root of the polynomial lambda squared plus lambda plus 1. So if we add and subtract 1 from this, we'll get rho squared plus rho plus 1 minus 3. And of course, the rho squared plus rho plus 1 becomes 0, and we're left with minus 3. So this tells us that when we multiply the top row by rho plus 2, we'll get rho plus 2 and minus 3. So when we subtract rho plus 2 times rho 1 from rho 2, we'll get the matrix 1, rho minus 1, 0, 0. This tells us the eigenspace E rho is cut out by the equation x plus rho minus 1 times y is equal to 0. So we can think about this eigenspace as being spanned by a complex eigenvector with entries 1 minus rho and 1. Scale this by 2 to clear everything out and make our numbers a little nicer. If we treat the complex number I like a scalar, then we can split this into two real vectors, and we'll call these two vectors v1 and v2. Since we're thinking about I like a scalar, we're going to take the matrix A, and we're going to multiply the vector v1 plus iv2 by A on the left. And we'll distribute this as av1 plus I times av2. This is, of course, the same thing as multiplying v by A on the left. And because this vector v is an eigenvector for A with complex eigenvalue rho, this is the same thing as rho multiplied by v. Now if we expand rho and v as complex objects, then just like multiplying complex numbers together, we can think about multiplying these complex objects together in the obvious way. We'll distribute the negative 1/2 to each of the terms, and we'll distribute the I root 3 over 2 to both terms. And so we'll get negative 1/2 v1 minus root 3 over 2 v2 as the real part, and the imaginary part will be root 3 over 2 v1 minus 1/2 v2. We can rewrite this as matrix multiplication. We can write the first one as the matrix with columns v1, v2, multiplying the vector minus 1/2 minus root 3 over 2. And we can write the second one as the matrix v1, v2, multiplying the vector root 3 over 2 minus 1/2. If they're going to be the same, the real parts have to be the same, and the imaginary parts have to be the same. So this will give us two equations. A times the matrix v1, v2, we'll get a nice expression. If we think about AV1 and AV2 as the columns of the matrix product, then A times the matrix V1, V2 is equal to the matrix V1, V2 multiplied by the matrix negative 1/2, negative root 3 over 2, root 3 over 2, negative 1/2. If we call this matrix with columns V1, V2, P, it's easy to see that these two points do not lie on the same line through the origin. Namely, one lies on the x-axis while the other does not. This tells us that P is an invertible matrix. So we can multiply our expression by the inverse of the matrix P. We get a similarity. And if we remember that rho bar is the complex number whose real part is negative 1/2 and whose imaginary part is negative root 3 over 2, then this matrix represents multiplication by rho bar. So if we had done this process with rho bar instead of rho, we would get the eigenvector W, which is twice the eigenvector 1 minus rho bar 1, which has a real component, the vector 3, 2, and an imaginary component, the vector root 3, 0. We would get another matrix, which we'll call Q. This matrix Q is also invertible, and we would see that A is also similar to the matrix representing multiplication by rho. A is similar to the matrix which represents multiplication by rho, and is also similar to the matrix that represents multiplication by rho bar. So, of course, you may be thinking to yourself, what in the world is going on here? If we dig into the algebra a little bit here, we can see what's really going on. So one way to do this is to recall that we can factor x cubed minus 1 as x minus 1 times x squared plus x plus 1. This second polynomial, of course, looks a whole lot like the characteristic polynomial. The only difference between them is this one uses x's instead of lambdas. But the factorization remains the same. This polynomial factors as x minus rho times x minus rho bar. So of course, this tells us that the numbers 1, rho, and rho bar are the three complex numbers whose cube is 1. And we call these the third roots of unity. Another interesting fact is we could actually check that either rho or rho bar will generate these three elements in terms of multiplication. So powers of rho will go rho, rho bar, 1, rho, rho bar, 1, ad infinitum. So of course, you can check that the two matrices that we've defined are related in the same way. So as a result, what we know about powers of matrices that are expressed in terms of similarity is that if we cube the matrix A that we started with, then we will get the identity matrix. Now, while the algebra may be surprising, geometrically, this should not be surprising at all. So if we consider the two complex numbers rho and rho bar as vectors in R2, of course, if we think back to a course in trigonometry, we should remember that the first one, rho, has coordinates cosine 2 pi over 3 and sine 2 pi over 3, while of course rho bar has coordinates cosine 4 pi over 3 and sine 4 pi over 3. Both of these vectors point towards the unit circle. If we view this in the right way, the relation rho cubed equals 1 is nothing more than the expression of the point negative 1/2 root 3 over 2 as a solution to the equation x squared plus y squared equals 1. So 1 is equal to rho cubed. We can pull off a rho squared and rewrite that as rho bar. So we get rho rho bar. Rho is negative 1/2 plus I root 3 over 2. And rho bar, being its complex conjugate, is negative 1/2 minus I root 3 over 2. If you don't already recognize this as the square of the modulus of rho, then you can apply the difference of two squares formula to see that this is negative 1/2 squared minus I root 3 over 2 squared. Of course, I squared is minus 1, and we're left with negative 1/2 squared plus root 3 over 2 squared. So that pretty much completes our tour through the world of complex eigenvalues.